All right, since we've already talked about torque, I want to segue into the concept of center of gravity. And I mentioned it a little bit when we did center of mass previously. Okay, and the motivation for this was if you have a meter stick, okay, we said, or we asked how many particles make up the meter stick. Okay, there's many, right? Avogadro's number of particles, 10 to the 23rd. So for a meter stick, instead of drawing, okay, all those little mg's due to each little atom or particle making up the stick, okay, this meter stick is equivalent to one mass right there at that geometric point, okay. That geometric point is called the center of mass, and this stick acts as if the net external force, which is the weight, acted at that point, and that point was called the center of gravity. Okay. Now we said if you were out in space where there's no planets, okay, you'd be in a weightless environment, much like if you're orbiting around the Earth. Okay. So if you were in a weightless environment, had a meter stick, and asked where would you balance in your finger, okay, you wouldn't talk about it balancing because everything is either it's a weightless environment, everything's falling, or if you're out in space, it wouldn't have any propensity to rotate or tip. So it makes sense to talk about a center of mass, let's say out in space, but maybe not a center of gravity in terms of trying to balance it on your finger. But for all practical purposes, let's say in the classroom, if you took the meter stick, the uniform stick, and trying to balance it on your finger, that point would be the center of gravity, okay? And they would be in the same position. So the center of gravity, center of mass would be in the same position, okay? Here's an exception. Okay, let's say I have a meter stick. Okay, there's my stick, meter stick, okay? So long meter stick, I have the earth below, and let's say there's a hole here, big cavity in the earth, and over on the right side, I have a huge deposit of gold. So on the left, I have a big absence of mass. Here I have where the gold is a lot of mass. So the gravitational field, okay, the little g, okay, due to the Earth, would be much stronger on the right side of the stick due to the gold, gravitational attraction, okay, then be much larger on the right side, gravitational attraction, than compared to the left side. So little g would be stronger over here on the right compared to g on the left. So in the picture of the stick up here, okay, center of mass is still in the same place, right? Because the atoms of the stick hasn't changed. But the center of gravity, since little g is larger on the right side of the stick, the center of gravity would be now at this point, meaning if you tried to balance the stick on your finger would be over at that point, the center of gravity. Okay, so that's an exception where they don't reside at the same point. Okay, so we're just going to say for all practical purposes, okay, well, the other reason is that the center of mass and center of gravity are not the same point is because in this example, g, little g, is not constant over the stick, okay? For our purposes, little g is constant over the surface of the object, okay? So that's why the center of gravity, center of mass will be at the same point for our handheld objects, all right? Okay, so down here I have an example. I have a plank of mass M1, like a board, and I have a person of M2 standing on the board. So I'm going to draw the forces on the plank. Okay, so I have the weight of the plank, okay, down, right? That's the mg from all semester. I have the weight of the person, okay, pushing down on the plank, all right? So essentially I have two forces, okay? So the weight of the person, weight of the plank. So this picture here, okay, would be equivalent to this. So I have the plank, I have the person, okay, and the center of gravity, right? So the total weight of the system appears to be acting right at that point where the total weight is m1 plus m2g. So the weight of the person plus the weight of the plank. So another way to look at this picture is, let's say I have the plank, okay, and let's say the plank weighs 100 pounds. This is a nice number. And the person weighs 100 pounds, all right? And again, it's a uniform plank, okay? Center of gravity is in the middle of the plank. Let's say you want to balance this system on your finger, okay? Well, where would you put your finger? Well, somewhere between the center of the plank, okay, and where the person is toward the outer edge. So this is where the center of gravity is shown, okay? So that's where you'd put your finger to balance the system, okay? Now, I would ask, well, what force would your finger have to support, meaning, or what force would your finger have to exert to balance it? or to hold it steady. Okay, well, your finger would have to exert a force of 200 pounds. All right, so if the plank weighs 100 pounds, the person weighs 100 pounds, you're going to be holding this thing and it's going to weigh 200 pounds. Okay, so this picture now looks like this. Here's your finger. Okay, and your finger thinks it's holding something that weighs 200 pounds. Okay, so if you turned out the lights, okay, for this picture, if you turn the lights off, okay, you couldn't tell at the tip of your finger whether you have a 100-pound plank and a 100-pound person, okay, or if you just have a 200-pound weight at the tip of your fingers, okay. So even if you kind of move them up and down, we know that from the concept of inertia, okay. If you move them up and down, okay, the 200-pound block moving up and down is going to feel the exact same as the 100-pound person and the 100-pound plank. Those two things are the same. You can't tell which one you have in your hand. Okay, and if I take the plank and the person and put it on the scale, okay, scale reads 200 pounds. Okay, well, this scale here has no idea whether you have a plank and a 100-pound plank and a 100-pound person, or whether you have one 200-pound weight sitting on the scale. Those two systems are equivalent. Okay. Now, how do we calculate the center of gravity? Okay, so here's the person in the plank, right? And so what I did is I drew the forces on the plank. So I have the weight of the plank, I have the weight of the person. Okay, and I'm going to pick an axis about which to apply torque. So I'm going to call the end of the stick here axis A, and on the right side over here, okay, I know that the plank and the person, okay, is equivalent to one mass, this is mass m1 plus m2, located at some point which I'm trying to find, called the center of gravity. Okay, so I'm trying to find the x location of the center of gravity, and I called this axis B to distinguish it from the left picture. Okay, so since these two pictures are equivalent, okay, so two masses over here, okay, let's say 100-pound person, or 100-pound plank, 100-pound person, or a 200-pound point mass, okay, those two forces are going to exert the exact same torque about the axis at the left end of the stick. So I'm going to write down the torque for each picture about each axis. So the torque about axis A, remember torque is force times the moment arm. So there's my weight of the plank. X1 is my moment arm. Remember the moment arm is a perpendicular line from the axis of rotation out to the line of action, so that's my X1. And then the torque due to the person is the person's weight, m2g, okay, times their moment arm, which is the whole distance from the axis of rotation, okay, out to where the line of action is. So I called that first one X1, I call this one X2 for person 2. Okay. Now when I calculate the torque about axis B due to the equivalent point mass m1 plus m2, okay, we have the weight, okay, remember that's the force, okay, which is the weight of both, that'd be my 100 pounds plus 100 pounds, or 200 pounds, okay, times the moment arm. So my moment arm, there's my perpendicular distance from the axis of rotation to the line of action. My moment arm is, that's what I'm trying to find, right? That's my moment arm. That's my X center of gravity, okay? Well, these two torques are equivalent. So I'm going to equate torque about axis A to the torque about axis B. So I equated that one and that one, wrote them down here, and then I solved for the X coordinate of the center of mass. Okay, just do the algebra. And then M1G is the weight of number 1, M2G is the weight of person 2, and then on the bottom I wrote weight 1 plus weight 2. And then I just wrote this in its compact form. Okay, if I had 3 things, I'd have to add weight 3 plus x3 and another one on the bottom, okay, and so on. Okay, I'd have to do that. Okay, so this is how you find the coordinate of the center of gravity, right? And it reminds you of when we did center of mass, but center of mass look like that. Okay, so here, to find the x coordinate of the center of gravity, you go to each object's coordinate, multiply it by its weight. Okay, add them all up, and then divide by all the weights of the object. Okay, now when we did center of mass, I said I done, I think, with 2 tennis balls on the road, and we argued that for 2 tennis balls, they're equal. The center mass would be at the middle, and I just kind of gave you that expression. And I said at that time it wouldn't be till we got to the section on torque that we'd be able to derive it. Okay, so to find the x coordinate of the center of mass, I take this expression here, okay, and I cancel out all the g's. So I could cancel out the g, the g, the g, and the g. So all the g's cancel, and then all I'm left with is I have m1x1, okay, and then I have m2x2, there's my m2x2, and the bottom I have m1 plus m2. That one's the same expression that I used but didn't prove for the center of mass. Okay, so once we look at what the center of gravity is, okay, when you divide out the g's, cancel all the g's, you wind up with the expression for the center of mass. Okay, here's an example of how we use the concept of torque. Okay, so in this picture, all right, we're going to ignore the mass of the meter stick. Okay, later on we'll include the mass of the meter stick. Okay, so we have a 100-gram mass, okay, M1, at the 30 centimeter mark on the picture. Okay, and the meter stick is pivoted, meaning it's supported at the 51 centimeter mark. It's kind of hard to see, but if you blow the picture up, okay, right where the center of that is, it's about 51 centimeters. Okay, so right now I just have that mass and the meter stick, and I want to put that mass on. And so I want to know, where would I have to place mass 2 of 50 grams such that the system balances? Okay, so this is just like 2 people sitting on a seesaw, right? You have 1 person there, okay, and obviously the other person now has to sit somewhere on the right. Okay, so for the system to balance, that means the system is in equilibrium. Okay, and I think we used that term earlier when we did Newton's second law. Okay, equilibrium also means that the net force is 0. Okay, we're also going to see that equilibrium means that the net torque about some axis is 0. All right, so since the system isn't moving, okay, and again, this reminds us of earlier. Okay, if you had an object sitting here that's not moving, velocity 0, acceleration 0. Okay, that means the net force on it is 0. Okay, the system is in static equilibrium. It's not moving. So if the system isn't moving, then the net torque about any axis has to be 0. So what we're going to do is we're going to calculate, or we're going to write down all the torques. All right. So remember, torque is force times the moment arm. So I picked my axis, and my axis is right where the support point is. I call that axis A. Okay. And so I'm going to draw the forces that act on the stick. All right, and again, we're going to ignore the mass of the stick for now. We'll do an example right after this where we include the mass of the stick. Okay, so here's my M1G, okay, acting at that point right there. Okay, I have M2G, okay, again, I'm trying to find this distance. Okay, I'm trying to find that distance on where to put that mass. All right, and then I have the support point. Okay, I have the normal force. Okay, the support point. Okay, that's the axis or the support pushing up on the stick. Okay, so I want to calculate the net torque. So what I did here is I'm going to calculate the net torque about axis A. And since it's not rotating, I know the net torque is 0. Okay, so a couple things we have to do. Just like when we did Newton's second law, okay, okay, part of the 5-step method is you drew the forces, we did that. Then you have to pick a coordinate system. Well, with torque, you also have to pick a coordinate system. You have to choose whether or not a certain force, let's look at M2, whether that force M2 would tend to rotate the stick downward or tend to rotate the stick upward, okay? So instead of talking about downward and upward, we use the terms clockwise and counterclockwise, okay? So if M2, okay, the force M2G, okay, imagine that's your hand, and your hand's pulling down, okay? That would tend to rotate the stick downward, which is clockwise, okay? Remember, that's clockwise, okay? All right, so if your hand was on the stick and you're pulling upward, that would tend to rotate it counterclockwise. So what we're going to do is just like we pick up is positive and down is negative, okay, when we did forces, we have to choose a direction for clockwise and counterclockwise, okay? So now, what we're going to do different than what the book does, okay? The book is really strict in terms of it goes back to geometry class, okay? And what the book does is the book says, okay, that's 0 degrees, 90, 180, and so on. So what the book does is it says, okay, angles are always positive going counterclockwise. So for example, that's 30 degrees, 90 degrees, 180 degrees, and so on, okay? So it says that any angle or any rotation that's counterclockwise is positive, all right? Well, the problem with that is it always locks you into coordinate system. And if you have a problem like maybe a wheel, and the wheel is always rotating clockwise, okay, then that means your coordinate system is going to be negative, or the direction that this thing is rotating would be negative. And that's more cumbersome. So what we're going to do for this problem here is I'm going to choose clockwise to be positive. Okay, doesn't matter what you choose, but here I'm going to denote that clockwise is going to be positive. So in my picture, okay, down here, any force that causes that thing to rotate clockwise about axis A is a positive torque. Okay, so I'm going to write down my torques. So I look at my picture. I have three forces. I have M1G, normal force, and M2G. Okay, all right. And again, here's my axis A, and I ask for M1G. Okay, M1G is downward. Okay, so again, you can even think of this like the wrench problem. All right, so your hand would be here. You'd be pulling downward. Okay, there'd be a bolt at the axis. All right, so if your hand is going downward, the force is downward, that would tend to rotate the stick counterclockwise about axis A. Okay, that'd be a counterclockwise torque. So that would be negative. Okay, M2G, we said, would tend to rotate it clockwise. Whoops. Clockwise. Okay, clockwise. And I'm choosing clockwise to be positive. Okay. If I look at the torque due to the normal force, so I redrew it over here. Here's the normal force, and it's acting right through the axis of rotation. So its moment arm is 0. Okay, so the normal force causes no rotation. Imagine if you only had the meter stick balanced on your finger. There's the meter stick, there's your finger. Your finger would be the normal force. Okay, the stick isn't rotating at all, so that normal force doesn't cause rotation. Okay, so I'm calculating all the torques, and I'm doing force times the moment arm. And I called clockwise positive, counterclockwise negative. So it doesn't matter which one I write down first. I'm just writing down my positive one first. So there's my M2G, that's my force. Okay, moment arm, okay, so moment arm for force 2. All right, there's my moment arm 2. And then my counterclockwise torque is M1G. That's my counterclockwise torque. So there's my force, M1G, there's my moment arm. Okay, and I'm trying to find where to place M2. So I'm trying to find my moment arm number 2. Okay, now all I did is I just brought this term over and I wrote it like that. Okay, all right, so what this says, okay, this was my clockwise torque. That was my counterclockwise torque. So when we did this, when we said the net torque about axis A was 0, okay, that's what we did here. Okay, when I say the net torque equals 0, that's the exact same thing, okay, we found from this algebraic step as writing net torque clockwise equal net torque counterclockwise. And it's nicer because then all your negatives wind up, okay, on the right side. So all the positive torques are equal in magnitude to the negative torques, okay? Okay, so all I did is I took this expression and solved this for R2. I'm trying to find the location for mass 2. So I put that right there. Okay, there's my R2. Okay, so all I did is I divide it by M2G. Okay, oh, and I canceled out my G's. Okay, so I rewrote this. Okay, and I canceled out my G's and solved this for R2. Okay, so I know the masses, but I need to figure out what's the moment arm for object number 1. Okay, so I go to the picture. Okay, so number 1 is at the 30 centimeter mark. The pivot point is at the 51 centimeter mark. So my R perpendicular is 21 centimeters. Okay, that's what I did here, 21 centimeters. So there's my, there's my mass 1, 100 grams. There's my R perpendicular 1, okay, my 21 centimeters. Divide it by my mass 2, 50 grams, and I wind up with 42 centimeters. So that's my 42 centimeters. That's my moment arm for mass 2, okay? Now, up at the top, I was asking or trying to find where would I place mass number 2. Well, if the moment arm is 42, okay, right, that's 42 from the axis of rotation. So the axis of rotation was already at 51. So I have to add 42 to that. So that says I place it at the 93 centimeter mark. So if I go back to the original picture, okay, sure enough, okay, number 2 is placed at about the 93 centimeter mark. All right, here's a torque example where I have a meter stick, okay. I have 3 masses, M1, M2, M3, okay, and they're hung at a specific point, so 20 centimeters, 55, 77, okay. There's my 20, there's my 55, there's my 77. There's a little bit of angle, okay, due to how the picture was taken, but that's at 77, okay. Okay, and so here, the stick is not rotating. It's at rest, okay, so it's in equilibrium, all right. And now I want to calculate the mass of the stick, okay, m sub s, the mass of the stick, based on, I know all the individual masses and I know where they're located, all right. So what I did is I just redrew the picture, okay, and I drew all the forces acting on the stick. So here's the weight of number 1. Here is the weight of number 2, the weight of number 3, okay. Here's my support point right there. There's my support point, okay. So I have the normal force pushing up, okay, normal force exerts no torque about that axis. Okay, now I'm not ignoring the mass of the stick. So the stick is uniform, so the mass of the weight of the stick, okay, the mg of the stick occurs right at the 50 centimeter mark, right there. Okay, so that's where the weight of the stick is. Okay, so the weight of the stick occurs at the center of the stick. Okay, so we're going to do this the same way we did last time. I'm going to draw the forces on the stick. Okay, so those are all shown. Okay, so I'm going to pick an axis of rotation about which to apply torque. All right, so the stick is not rotating, but it could rotate about the pivot point. So I'm choosing the pivot point as my axis of rotation. Okay, draw the moment arms. Okay, so remember, here's my line of action for M1G, and I have to draw a perpendicular line from the line of action to the axis of rotation. Okay, that's that line right there, R perpendicular 1. So I did that for number 1, I did it for number 2, okay. Number 3, I put it up here so it wouldn't be in the way. Okay, and then R perpendicular for the stick is from the axis of rotation out right there, out to where the center of mass of the stick is. Okay. Okay, now when I apply net torque equals 0 about axis A, right, so some torques are plus, some torques are minus, right, then I said that's equivalent to saying net torque clockwise equal net torque counterclockwise. Okay, so in this picture, I'm just going to say if anything rotates the stick clockwise, that's a positive torque. Okay, so the good thing when I do clockwise equal net torque clockwise equal net torque counterclockwise, I don't have to think about pluses and minuses. I just have to think of clockwise and counterclockwise. Okay, so looking at the picture, what are my clockwise torques? Okay, well, I know that everything on the right side would tend to tip the stick downward. Okay, that's clockwise. So I have the weight of the stick, that's the weight of the stick, times its moment arm. I have weight number 2, times its moment arm. I have weight number 3 times its moment arm. That's all my clockwise torques. And then remember, the normal force causes no torque. Right? Torque due to normal force is 0 because that force passes the axis of rotation, has no tendency to cause rotation. There's no twisting associated with that force. Okay, and then my only Counterclockwise torque is due to M1G. Okay, so the M1, the downward M1G force would tend to rotate the stick counterclockwise. Okay, so that's why that one's right there. Okay, and then what I had to do in the pictures, I had to calculate all the moment arms. Okay, so I look at R perpendicular number 1. Number 1's at the 20 centimeter mark, and the axis, the stick. Okay, I know it's hard to see in this picture, but the stick is actually pivoted at the 40.5 centimeter mark. So to find R1, I had to do 40.5 centimeters minus 20. That's what I did here. Okay, so I found the distance from where M1 is hanging to where the pivot point is. And I did the same for the stick, okay, because the center of mass of the stick is at 50, but the pivot point's at 40.5, so the distance between those two is that. Okay. For M2, M2 is hanging at the 55 mark, but the pivot point, okay, is 40.5, so that's my R perpendicular 2. And then mass number 3 is hanging at 77, okay. All the moment arms are drawn from the axis rotation, which is 40.5, okay. So that moment arm is that. Okay, so then what I did is I took this expression, okay, and I solved it for the mass of the stick. Okay, just do the algebra. Okay, and then I put in each mass, each moment arm, okay, and I found that's the mass of the stick. Okay, all right. So, and that's another way to measure an object's mass. Okay, we did the Newton's Law lab where you accelerate the glider. Okay, you vary the force. We plotted acceleration versus force. You found the slope of the line, and then you inverted that slope to give you the inertial mass. Okay. Here's another way to measure something's mass. You can actually hang things from it. Okay. Pivot it about a certain point, and you can actually calculate the unknown mass of a stick using the concept of torque.